Hello, welcome to Meki Techie. Learn as engineer, teach as champion. First of all, I would like to thank my family for their continuous support and encouragement for creating these kinds of technical videos and posted into a public domain. And I would like to thank my mentor, Professor R. Surendran from Government College of Technology, Coimbatore, for igniting me and sparking me to creating these kinds of technical videos. And I would like to thank Almighty for my health and my prosperous mind and friends, followers, my dear students and subscribers. Today's topic of interest is vibration. I would like to give a brief explanation of a vibration. Vibration is a aperiodic motion having a small magnitude, or we can call it as a small amplitude. The vibration is a fourth derivative of the displacement. We can know that the displacement is in the form of S. If we derivate or differentiate the displacement with respect to time, we get a velocity, and d square s by dt square is equal to acceleration, and d cube s divided by dt cube is called as a jerk, and d power 4 divided by dt power 4 ds power 4 divided by dt power 4 is called as a vibration. It is a differentiating format of a jerk is called as a vibration. So with this background, the vibration, an example of a vibration is everywhere. If you are riding a vehicle, you can feel the vibration, a small unwanted and amplitude of motion. This is called as a vibration. In everywhere, even our earthquake is one type of a vibration, where if the amplitude is more, if it make it to resonance condition, it will demolish all the things about the earth. So with this example in the background, I would like to touch upon vibration. As I said earlier, vibration is a periodic motion of a small magnitude. Here it is in the form of a simple harmonic motion of small amplitude. Mostly springs, beams and shafts are absorbed by the vibrations. Wherever we are using spring or a beam or a shaft, the vibration is occur. And the vibration can be derived by a spring mass system or a shaft torsion system or a transverse system. First of all, we have to know certain definitions in the vibration. First one is the period. Period is the time taken by the motion to repeat itself and measured in seconds. Once the period is the time taken by the motion to repeat itself. If we say this is my amplitude, so having a positive and negative sign, if the third quadrant it is going to repeat the first, this is 1, 2 and 3 will going to repeat the first. So this is called as an period, and where this is called as an amplitude. So the total is called as an amplitude. The maximum extent of vibration or oscillation is measured from the position of equilibrium. So this is the position, equilibrium position. So here, if we in the positive sign, this is the maximum one. Therefore, this measure quantity is called as an amplitude. In negative sign, this is the maximum. Therefore, this is called as an another amplitude. And the frequency is the number of cycle of motion completed in 1 second. This is one cycle. One cycle consists of one positive and negative thing, and these kinds of number of cycles, number of positive and negative cycles which are completed in 1 second, which is called as a frequency. And time period, for information, time period, it is an inverse of frequency. The frequency is measured by means of a hertz or cycles per second, whereas the time period is measured in the seconds per cycle. And the last and important definition is resonance. Resonance is the frequency of external force is the same that of the natural frequency. If the natural frequency f of n is equal to the external force, here if the natural frequency f of n is equal to the external force, then it will becomes resonance. Resonance is the it is a large amplitude of vibration. It is a dangerous one. Resonance is the dangerous one. The earthquake or by means of the resonance, if it goes to the resonance, the damage is huge. Okay, next we are going to see the types of vibration. We have a free vibration, forced vibration, in the linear vibration, transverse vibration, and a torsional vibration. Here first we are going to discuss free vibration. The free vibration and forced vibration will come along with the all the three major classifications, that linear, transverse, and torsional. All the things we have a free as well as the forced vibration. Where first of all we are going to discuss free vibration. Free vibration means there is no friction and there is no external force. In free vibration, we have two different types of free vibrations. One is damped free vibration, another one is undamped free vibration. So, what is the difference between damped and undamped is? For your information, consider this is a spring mass and dashpot system. Here, this is my mass, this is my dashpot. Dashpot is nothing but a shock absorber. Okay, it having an oil, and this is my spring K. Whereas undamped vibration is there is no dashpot between the mass and spring. Only mass and spring are available in the undamped vibration. And in the damped vibration, since there is a C dashpot, it will produce resistance, because in the dashpot, oil kind of a fluids are used. Generally, fluids having viscosity, therefore resistance is possible, and the vibration is gradually dissipated by means of friction, or we can say it as an resistance. And in the undamped vibration, there is no friction and there is no resistance. Therefore, the governing equation for the damped vibration is mx double dot plus cx dot plus k into x is equal to 0, whereas for the undamped vibration, mx double dot plus kx is equal to 0. Here we can say in some of the books they provide in x double dot that is equal to d square x by dt square. That is the meaning. Whereas x dot means dx by dt. So it is a form of a derivative, nothing. Okay, here with the undamped vibration, we go with the further one, and the natural circular frequency, that is omega n is equal to root of k by m, and linear frequency, which is f of n is equal to 1 by 2 pi root of k by m. And with considering the mass of the spring, when we consider the mass of the spring is also in the position, therefore the linear frequency will becomes f of n is equal to 1 by 2 pi root of k divided by m plus m1 by 2. Here the m represents the mass which is hanged, and the m1 represents the mass of the spring. And the longitudinal vibration is the vibration when the particle of a body moves parallel to the axis. See, if we have a spring mass system, When it is said to be an longitudinal vibration, the vibration should be parallel to the axis. So this is the axis and the vibration is parallel to the axis. So this kind of vibration is called as longitudinal vibration. Longitudinal vibration. And next one is the damping factor. When it is a damped vibration, the damping factor will come into picture, where damping factor eta is equal to C by Cc, which means damping factor is the ratio of actual damping coefficient divided by to the critical damping coefficient, where critical damping coefficient we can say it is 2 into root of k into m. 2 root of km is the uh, critical damping coefficient, and when the eta will come into picture, that is c divided by 2m omega n. This km we can convert it into omega m into omega n. That is possible. Okay, and here we have a, when the springs, this is the important one, the springs are in parallel and series, we have to find the equivalent stiffness. Therefore, parallel springs, the equivalent stiffness is having K1 plus K2, and the series springs having K equivalent is equal to K1 K2 divided by K1 plus K2. And with the damping frequency or damping factor, we can subdivide the vibration into, or damping is into, three kinds. One is critical damping, and another one is over damping, and another one is under damping. Where in the critical damping, it is a quick process, non-oscillatory damping. The thing or a body can easily become to the original position without any motion. Here, these kinds of vibrations are available in a heavy gun field. Okay, if we are having a gun, okay, when we are firing it up, what will happen? The gun will again quickly come into original shape and original position without any vibration. If there is no critical damping, what will happen? Due to the force, due to the thrust of the bullet, the body will continuously disturbing and continuously having motion. Therefore, the next bullet will not come into picture. This is a similar way when where there is a military tank, they are launching a huge amount of a bullet to the opposite country or an enemy. The system, the complete system should be critically damped. Then only the quick firing will be happening. And here the for the critical damping, the damping factor is equal to 1. When the damping factor is more than 1, what will happen? It is over damped system. It will becomes over damped. That is, critical damping or an actual damping is more than critical damping. Critical damping becomes small. That is, it is a dead slow process. In some of the offices, we are having a cabin room. In the cabin room on the top, we have a door closure, automatic door closure. When we open the door, if you can visualize, the door can slowly come into the original position. So that is called over damped system. When this damping factor is less than 1, then your actual damping coefficient is smaller than critical damping coefficient. Then this is called as an underdamped vibration or an oscillatory vibration or a slow process, where very slow vibration is happening. Very slow vibration is happening. It won't come into the original position. It take very long time to come into the original position. That is called underdamped vibration. And next, the logarithmic decrement. When we say an underdamped vibration or a damping factor, we have an logarithmic decrement curve, that is, in any spring mass damper system, the vibration, the frequency of vibration will keep on reducing. So this reduction in the form of logarithmic factor, the form of logarithmic factor. This is exponentially decreasing in curve. That is why the logarithmic decrement is the two successive amplitude of the same side of the mean position. Therefore, the logarithmic decrement is mentioned in delta. For delta is equal to 2 pi into damping factor divided by square root of 1 minus damping factor the whole square. And here we have another formula, that is delta is equal to ln, natural logarithm of ln of xn divided by xn plus 1. If we consider the logarithmic decrement of the first and second oscillation, the n becomes 1 and the n plus 1 becomes 2. Therefore, the formula becomes delta is equal to ln of x1 by x2. Okay, so that is all about the free vibration. Next, the forced vibration. The difference between the free and forced vibration is there is an external force which is applied and creates the vibration, or the frequency of vibration that of the applied force and independent of their own natural frequency. Due to the applied force, the vibrating body will not make their own natural frequency, so that is called as an forced vibration. Here also we have two kinds. One is undamped and damped. The difference is, one thing is the Cx double dot is plays a vital role in damped vibration, whereas in the undamped vibration there is no dash spot. Since it is a forced vibration, in the right hand side we have a f naught sine omega t. It is a intensity of the forced vibration. Due to the forced vibration, we have two concepts come into picture. One is the magnification factor. The magnification factor is the uh, ratio of maximum deflection or displacement to the initial deflection, or we can say it is a ratio of maximum displacement to the initial deflection, or we can say another definition of the ratio of steady state response to the static deflection under the action of force. So that is called as an magnification factor. So here magnification factor is equal to x max divided by delta naught. Therefore, uh, the magnification factor becomes 1 divided by square root of 1 minus omega divided by omega n, the square and the whole square, plus 2 eta into omega by omega n the whole square, where omega by omega n is the frequency ratio. Since magnification factor can be also called as a dynamic magnifier, it is also called as a dynamic magnifier. Next, which we are going to see, transmissibility. Transmissibility zeta is the ratio of force transmitted to the ground to the applied force, that is called as a transmissibility. For your better understanding, transmissibility, when we are running a machine, say any lathe or a milling machine, during machining definitely there will be some vibration, or some vibration is produced. That is due to the machining, the force is applied on the body. We know that the lathe bed is made up of cast iron in order to absorb vibration. Even though it absorbs the vibration, in certain amount of vibration is transferred to the ground. So how much amount of vibration, how much amount of force is transmitted to the ground to the applied force which is called as a transmissibility. It is the measure of effectiveness of the vibration isolation. Even we have a late bed for making isolation, vibration isolation, but the 100 percentage is not possible. 100 percentage isolation is not possible. Even though cast iron, we know that cast iron is a good damper. Even though we have a cast iron in the lathe bed, we feel the vibration is surrounding the ground. So that is called force transmitted to the ground. Okay, the ratio is called as an transmissibility. The transmissibility, the formula is the square root of 1 plus 2 into eta into omega by omega n the whole divided by square root of 1 minus omega by omega n the square to the whole square plus 2 eta omega by omega n the whole square. If it is in a resonance condition, the resonance condition means omega is equal to omega n, then zeta is equal to square root of 1 plus 2 into eta the whole square divided by 2 eta. When there is no damping, the transmissibility becomes 1 divided by plus or minus 1 minus omega by omega n the whole square. Here we have a relation that the damping or frequency ratio and the transmissibility relation, when we get this omega by omega n is less than root 2, the transmissibility is greater than 1, and where the omega by omega n, and the omega by omega n is greater than 2, then the transmissibility is less than 1. That is, it is reciprocal, okay, inversely proportional like kind of thing. The frequency ratio and the transmissibility are the inversely proportionals. When the omega by omega n is equal to square root of 2, then the transmissibility is equal to 1. I hope that you all understand the linear vibration. Next, we go with the transverse vibration. The transverse vibration, the particle moves perpendicular to the axis. Say, when I have a spring mass damping system, this is mass, this is stiffness. When I have a frequency of this kind, this is the axis, and we have a parallel to the axis, it is called as an linear vibration. And we have a perpendicular to the axis, that is called transverse vibration. If my spring mass damping system is oscillating like this kind of a motion, then it will becomes transverse vibration. For the transverse vibration, the natural frequency is omega n is equal to square root of g by delta, where g is the acceleration due to gravity. We all know that 9.81 is the value, and delta is the static deflection. And next one, whirling of shaft. Due to the transverse vibration, whirling, the most of the transverse vibration are occur at the shafts, where the whirling of the shaft is a huge problem on the transverse vibration. That is why we are concentrated on here. The whirling of shaft y is equal to e divided by omega n divided by omega the whole square minus 1, where y is the displacement of the shaft from axis, where e is the distance by which the center of mass of the shaft is displaced from the center of axis. At the resonance condition, the omega is equal to omega n. Here, the omega c, which is equal to omega n, that is equal to square root of k by m, becomes g by delta. That means at the resonance condition, the transverse vibration becomes linear vibration, where we know that k is equal to load by deflection. We know that k is equal to load by deflection, where from w we have a weight becomes mass into gravity divided by deflection. Therefore, instead of k by m, if we substitute mg divided by m into delta, then the transverse vibration formula will becomes, that is omega n is equal to square root of g by delta. Here, when the omega n when the omega n is less than omega, then your whirling of shaft y is less than 0, that is vibrate in opposite direction. If y is equal to minus e, that is minus eccentricity, the shaft will immediately stop vibration. The shaft will immediately stop vibrating. And the most accurate method to find the transverse vibration is Dunkerley and energy method, where the Dunkerley formula, which can be narrated by 1 by f of n the whole square is equal to 1 by f of 1 the square plus 1 by f of 2 the square, and goes on. So this is the Dunkerley formula, and here we have a formula. By substituting or by interchanging the formula, above formula, we can get these kinds of a formula. When the f of n is equal to 0.4985 divided by square root of del 1 plus del 2 plus del 2 del 3 up to the shaft, delta shaft divided by 1.2927, and if there is no mass of the shaft, f of n is equal to 0.4985 divided by square root of delta 1 plus delta 2 plus up to the n. Here if there is a eccentric cantilever beam, if there is a eccentric cantilever beam condition, then your delta becomes w1 a1 square into b divided by 3EIL, where if there is a condition of a simply supported beam, the deflection delta will becomes 5 by 384 W L power 4 divided by EI. So this is for the point load condition, and this is for the uniformly distributed load condition. And next one is the torsional vibration. When the particle moves in a circular direction, okay, we having a shaft kind of thing like this. If it is rotating by means of an oscillation, it is called as a torsional vibration. A twisting kind of a motion will come into picture. Here the torsional stiffness is coming to picture. Torsional stiffness is equal to Gj by L. Therefore the governing equation becomes I theta double dot plus q theta is equal to 0, where the natural frequency omega n will becomes square root of q by I, and the frequency will becomes 1 by 2 pi square root of q by I. Here the inertia effect of the mass of the shaft will, if there is a consideration, then f of n is equal to 1 by 2 pi square root of q divided by I plus I1 by 3. Here I is the inertia of the shaft, I1 is the inertia of the spring. Here the torsional equivalent shaft, the equivalent length is an important thing. The length of the equivalent shaft L is equal to L1 plus L2 into d1 by d2 the whole power 4 plus L3 into d1 by d3 whole power 4. And here we have a long thing you have to remember in the vibration. First of all, in the longitudinal vibration, stress is induced in the body, which is like a tensile and compressive in nature. Whereas transverse vibration will have a bending stress. And the torsional vibration will induce the shear stress. And we have a condition in the spring stiffness is half, the mass is doubled, the natural frequency will becomes Fn divided by original divided by half, or the half of the original frequency will come. And next, critical speed of a shaft in the revolution per second is the same that of natural frequency of the transverse vibration. the critical speed of a shaft is equal to natural frequency of transverse vibration. And also, critical speed of a shaft is depends upon mass and stiffness. You have to notice this. This is an important thing. The critical speed of the shaft is depends on mass and stiffness. We can remember by means of a mnemonic code. MS, we know that master of science. MS படிக்கிறதுக்கு கிரிட்டிக்கலாக இருக்கும் அப்படிங்கிறத ஞாபகம் வச்சுக்கலாம். ஸோ திஸ் இஸ் த ஷார்ட்கட் ஃபார் ஸ்டடியிங் MS. It is bit critical. And the next one, factors affecting the critical speed is diameter of the disc, length of the shaft and eccentricity. Next one is the danger of breakage and vibration is maximum near the critical speed. When the shaft is at the critical speed, there is a danger of vibration as well as the danger of breakage. When we have a condition next, the rotating shaft tend to vibrate violently at the whirling shaft. It is because of resonance caused due to heavy mass of the rotor. And also, as a critical speed, the critical damping is the function of mass and stiffness. Here you have to notice that critical damping is the function of mass and stiffness, whereas critical speed of the shaft is depends on mass and stiffness. You have to understand. In underdamped vibration, the amplitude of vibration decreases exponentially with time. Here, like this curve, the vibration will keep on decreasing by means of exponentially. And next, a mass of a critically damped single degree of freedom system deflected from its equilibrium position and it is released. It will oscillate with the increasing time period. When the critically damped single vibration will increase the time period. And next one, the logarithmic decrement, the amplitude of the successive vibration are in the geometric progression. Here, the nodes are coming to picture. The node of the shaft remains unchanged by the vibration. This is the important concept in the whirling of shaft. This is a small kind of a thing. We have a two rotor system. If a shaft having two rotors, the number of nodes will have the capital N is equal to N minus 1. Here small n indicates number of rotors. If our system is having two rotor system, then the number of nodes become 1. There is a three rotor system if the number of nodes will have 2. And the next one, the methods used to determine damping of machine elements. We have two methods. One is a logarithmic method, another one is a bandwidth method. Here I have narrated the what happen if the parallel springs are placed. The vibration natural frequency will becomes, the formula will becomes like this, and the damping logarithmic decrement, the graph I have shown here. Next one, critical speed of a uniform shaft with a rotor at the center of the span can be reduced by increasing rotor mass. The critical speed of the single rotor system can be reduced by increasing the rotor mass. Next one, the spring mass dashpot system is subjected to excitation by a constant harmonic force. Then at resonance, the amplitude of vibration is inversely proportional to damping, as I said earlier. And next one, the forced vibration, the damping, maximum amplitude occurs when the frequency is slightly less than natural frequency. And the natural frequency by Rayleigh method is always greater than actual fundamental method. Rayleigh method always gives more vibration. Rayleigh method is a mathematical method to finding the vibration. That is for your information. Next, torsional vibration of a shaft. The nodes are characterized by, in the nodes there is no or zero angular displacement. At the node there is no displacement occurs. The whirling of shaft is caused by non-homogeneity of the shaft material. This is an important thing. Wherever the whirling is happen is due to non-homogeneity of the shaft material. Next, the viscous damping will gives a periodic motion to the vibrating body in underdamped vibration. Here, for the underdamped vibration, it is a periodic motion, where the critical and overdamped motion, it is having aperiodic motion. Here, I have given an example of a critical damped system. A large gun field, a large gun field will have with come to initial position after firing a shortest possible time, which is done by critical damping. Next one, free vibration with viscous damping. The damping force is proportional to velocity. The damping force is proportional to velocity. And critical speed is expressed in natural frequency of the shaft, and critical speed of the turbine is depends upon the speed which is equal to natural frequency of the rotor. The linear vibration analysis have a greater advantage because of Newton's law of motion is used. The first critical speed of an automobile running with sinusoidal road is called as a resonance. That is the single degree of freedom system. And the rate of decay of oscillation, which is called as a logarithmic decrement. Here you have to notice this: the rotor of the turbine is usually rotated above the critical speed. Rotor of the turbine is usually rotated much above the critical speed. Okay, with this I am closing the vibration thing. I hope that I have given an enough idea or enough knowledge about the vibration. If you have any doubts, please let me know in the comment section. And thank you for watching. Thank you all. Have a nice day.